So our last math topic is actually a couple of just sort of random topics that don't fit elsewhere. We're going to talk a little bit about cycle finding and just mention a little bit about games. And neither of these is necessarily a math problem on its own, although they're both related to math, which is why we'll talk about them here. But they're more just a couple of random topics about types of things that can come up. So one of these is finding repeating cycles. And the idea here is that you have a process that's going to generate values or states or something like that. It's generating something, and eventually it brings you right back to where you were at some previous point. Now, it's not always the starting point. It might be some other point along the way, but you've got a cycle that then once you're in that, it's going to keep repeating over and over. And so there are two things that you often want to know, and they're usually referred to as mu and lambda. So mu is going to be your starting, I guess you would say the start of a cycle. And lambda is going to be the length of a cycle. In other words, how long does it take until the cycle repeats? Now, cycle finding, if you have a graph or something like that, this might not seem like a very difficult problem. The types of problems where this comes up, and it's a little bit trickier to think about, are when each of these points in a cycle is something that gets generated through a process, and you want to figure out, wait a minute, do I have a process where I've gone back to where I started at the beginning? And so there's a couple of broad approaches that you can use to find them, and they're useful in slightly different circumstances from each other. So the first one is you can store each state in a dictionary or a map or something like that. And then you can actually look it up. So every time you generate a new state is check to see, check if each new state has been seen before. So you look it up in the map or dictionary or whatever, you say, have I actually seen this state before? And if so, you can either, if you just need to know, is there a cycle? It will tell you where the cycle is. The first time you find a repeat, that's going to tell you what mu is. That's going to tell you your start of the cycle. And if you store the time or the step that each state is first found, you can get lambda. In other words, if I'm here and I say this is 1, 2, 3, 4, 5, 6, 7, 8, and then now I come back here to 9, well, I know the cycle is length 7. Okay, because first of all, this is going to be mu, is going to be that number 2, and lambda is going to be 9 minus 2, or 7. Okay, so that's one approach to doing this. Now, this is actually a very effective approach. It's probably the preferred approach, assuming you can store your states easily in a map. So if you can clearly say, here's my state, and I can put it into a map where I can look it up, that's great. That works perfectly. That's not always possible. And so sometimes you need to use Floyd's cycle finding. And this is one that often comes up if you have something like a linked list and you're wanting to find, do I have a cycle in the linked list? And how do I determine that? So you can imagine that you've got states with, pointers between them. And at some point, there's going to be a state that goes back and points to the previous one. And you want to know what that is. Well, the way that this can work is you can actually keep 2 pointers. And again, let me just emphasize, this does not have to be a standard linked list. These can be a state that you're in, like a whole bunch of variables or something like that. It might be something that does not map well into a hash table that you would need in a map. So you're going to keep 2 pointers. and let's just call them A and B. And at each step, we're going to advance A by 1 step, and we're going to advance B by 2 steps. Okay, so if we have a cycle like I'll draw one here. So let's say that I have this graph up here at the top. I'll use it. So blue is going to be A and green will be B. So we start out and both of them are pointing right here at time 1. So this is time 1. Okay, so at time 2, we're going to advance A by 1 and we're going to advance B by 2. Okay, at time step 3, we advance A by 1 and we advance B by 2. At time step 4, we advance A by 1 and we advance B by 2. So you're back here at 5. And then at time step 6, we advance A by 1 and we advance B by 2. And now notice that B and A are again pointing at each other at this point. Okay, and so that will tell you how long it took in order to actually find the point at which the cycle repeats. So the fact that A and B, if they ever line up, so if A and B are equal, and this will imply that you have a cycle. Okay, so therefore a cycle exists. And now you can get the values of mu and lambda from this information as well. So the basic idea here is that if you go around in a cycle and these two things end up meeting each other, one of them, the slow pointer A, will have gone I steps, and the longer pointer B will have gone 2 I steps. And what this means is that the cycle lambda is either equal to I or I divided by some particular value. So a way to look at it is K times lambda is equal to I. So the difference, that basically they've wrapped around to themselves in a distance I, and so I is at least a multiple of the cycle. Okay, so once you have that, you don't know what K is, so this might still be a multiple of the cycle. So to get mu, you can start pointer A at the beginning and pointer B at I, and then increment them both at 1 step at a time. And they will meet at mu. Okay, so once you know where they meet at mu, and then you can go ahead and just march around the cycle 1 time to figure out exactly what lambda is. So then you back to self, and this will give you lambda. Okay, so the point here with Floyd cycle finding is if you have something like a linked list where it doesn't necessarily make a whole lot of sense unless you've got a unique ID on each element of the list, you might not even be able to, store what the state is. You might not be able to put it in a hash table or a map of any sort. And so you can use Floyd cycle finding to kind of loop through and find a cycle. And this approach can be used in a variety of other situations where you're computing values. You don't want to store it in a state, but you want to actually just compute, hey, do I have a cycle? And if so, where do things repeat? Okay, so that's the cycle finding problem. The other topic that I wanted to mention briefly is a little bit about game playing. And there are problems that you'll see that are game playing based, and these have very real applications in a whole variety of real world situations where you're trying to model behaviors, or you're trying to optimize something, or you are trying to sort of converge to a fair solution. Often a game playing approach is a way that this works. And so one category of game playing is you get what you would call zero-sum games. And the idea of a zero-sum game is that either one person is going to win or the other person is going to win. And so the sort of, if one there, there can't be two winners, they can't cooperate, they can't both have some value like that. And so you're wanting to find basically who wins which game. And so typically these things can be expressed as a DAG, and more commonly, it is often thought of as a tree, although it's technically not a tree, where each node is a game state, and the edges represent moves. So for example, we might start out with the starting condition on the board, and there might be 3 possible moves for person 1, or 4 possible moves, and so that ends up with 4 states. And then for the next state, it's player 2's turn, and they might have 3 possible moves from here, and 2 from here, and 4 from here, and 4 from there. And each of those things then is going to create a new state, that it is now back to player number 1's turn. And so player number 1 then will have possible moves coming from each of them. And so you can think of this as a giant tree. This is why it's often thought of as a tree. Now, the reason why it's not technically a tree is sometimes some of these states, for instance, these two might actually be the same state. So technically, this is not necessarily a tree, but we often treat it that way in terms of analysis. Okay, and the typical way that this is represented is what's called a minimax tree. And you might have encountered this. Often it'll be in an AI class. And the idea is that at different levels of the tree, depending on whose turn it is, you're either trying to minimize the value of what's there, or you're trying to maximize the value. So one player is trying to minimize, one is trying to maximize. That's because it's a zero-sum game. They're going in opposite directions. And so, for instance, when it's player 1's turn, this might be a max node. And when it's player 2's turn, that would be a min. And then the next one here would again be a max, and so on, and it would alternate. And there are a whole variety of approaches for dealing with minimax trees. There are ways of doing what's called pruning. And pruning is where you basically can get to a point in the tree and say, wait a minute, there's an entire branch of this that, like, I can identify, hey, if I go here and I pick the minimum, well, nothing that I do from here on is going to work. And so I can sort of prune that entire branch away. And sometimes you can prune various pieces of this away, and it becomes much easier to search all the states than it might first appear. So there's pruning methods. Alpha beta pruning is one that you might have heard if you study this in an AI class. But the end result of this is basically, if both players play optimally, who's going to win? And there's a variety of heuristics and things like that that you'll use along the way. But the question is, who's going to win? And so the idea is you sort of explore this state space and try to kind of maximize from the bottom up. So when you get to the very bottom of sort of a path, you might say, well, if I get to this state, player 1 wins, or that state, player 1 wins. And if I get to this state here or this state here, player 2 wins. And so there would not be any children off of those, because there would be only a single winner possible out of them. And based on that, then, each player would know what to choose. So for instance, if purple was that player 2 won, well, this is player 2's turn. And so player 2 is obviously going to choose this choice. And so because there's a choice that player two knows leads to a winning condition, you don't even have to follow these other possible paths. There's no reason you would ever go down that route. And so you can stop early and so on. You don't have to explore, well, what if I made a bad move? Because player two would never make a bad move. They're going to play optimally. Okay, so that's one category of problems, or game playing problems. Again, they are a sort of, I'll say, common class of problems that have some very real applications. And I'll just mention that there's one real interesting game. It's one that comes up, and variations of it come up quite a bit, and that is the game Nim. And the idea of Nim is that you have different piles of stones, and the different piles might have different numbers of objects in them. So in this case, maybe I've got 3 piles, and one of them has 6, and one has 9, and one has 4. So there's 6 and 9 and 4. And basically, there's, again, slight variations on this, but the rule might be that a player can take any number of stones from any one pile. So you can only draw from one pile at a time. And the winner is going to be the person who takes the last stone. And so you can think, if you're playing, one thing you don't want to do is leave a single pile. You always want there to be at least two piles, because if you leave a single pile, the other person's going to win. Now, if you ever get to a state where there's just 2 stones like that, well, guess what? You have to take one of them, and then there's a single pile, and then the other person wins. And so you can sort of build this up. You can solve this with a dynamic programming approach. So you can actually kind of list out the different states that you have depending on the number of stones in the pile, and kind of work your way backward through a game like Nim. So DP is your friend here. However, there is a particularly interesting property of Nim, and if you want a real challenge, try to figure out why this is the case. I won't go into it, but you can look up why it's the case, but I would encourage you to think about it first. And that is, player one is going to win if and only if the binary XOR of basically all piles is not equal to 0. And this means that player one wins. Okay, and so it's a very weird property. It's not something you would first think about. So again, the binary XOR would be, if you've got a number like 6, that would be 1, 1, 0, and a number like 9 would be 1, 0, 0, 1, and a number like 4 is 1, 0, 0. And so if I take the binary XOR of all of these, I would have 1, 1, 0, 1, 0, 0, 1, and 1, 0, 0. And if I do the XOR of all of those, well, this is 1, this is 1, this is 0, and this is 1. So that is non-zero, and therefore player one can win this game. So player one can choose optimally and will be able to win. Whereas if you had something, for instance, if you had something that had 1 stone and one that had 5 stones and one that had 4 stones, well, you would have the number 1, you would have the number 5, and you would have the number 4. And if you take the XOR of that, it's 0, and therefore player 2 would win. Okay, so it's a very interesting property of Nim, but you can sort of solve the cases if you want to via DP and see how this would come out, and it might be useful to convince yourself that that's the case. Okay, so that's all we have. That's the end of our math topics. All these last couple of things about games were just to get you in the mindset of this is the type of problem that you might run into, but it's just a very general approach. There's not anything super specific beyond there.